Good. So here we go. Welcome everybody to Wednesday Night at the Lab. I'm Tom Zinnan. I work here at the UW-Madison Biotechnology Center. I also work for the Division of Extension, Wisconsin 4-H. And on behalf of those folks and our other co-organizers, PBS Wisconsin, the Wisconsin Alumni Association, and the UW-Madison Science Alliance, thanks again for coming to Wednesday Night at the Lab. We do this every Wednesday night by Zoom, 50 times a year. Tonight, it's my pleasure to introduce to you Lena Roald. She's a professor in the Department of Electrical and Computer Engineering. And I'm about to ask her the 5 questions. Lena, where were you born?
You can hear me. I'm not muted. Okay, yeah, yep. Great. So, no, I was born in Oslo, Norway.
Very good. And where'd you go to high school?
Also in Oslo, Norway. So I was in Norway until I finished high school.
And then where did you go for your undergraduate degree and what did you study?
So I left Norway and I went to Switzerland and I studied at ETH Zurich in Zurich in Switzerland. That was in my bachelor's degree was in mechanical engineering.
And then where'd you go for your advanced degrees?
So I stayed in Zurich and I went on to do also a master's of science in mechanical engineering. And then I got very interested that was related to wind power. And so I got very interested in the electric grid and how wind power kind of is transforming the electric grid. And I went on to do a PhD in electrical engineering focused on electric power systems, but also at the same university. So I switched department, but still in Zurich.
Very good. And then when did you come to Madison?
So I have been in Madison for about 3 years now, or it will be 3 years in August. So that's
great. Well, thank you very much for coming to speak to us at Wednesday Night at the Lab. Tonight, you're going to be talking about how to reduce the risk of wildfire ignitions from power grids. So I hope everybody will join me in welcoming Professor Roald to Wednesday Night at the Lab, and you can take it away whenever you're ready.
All right, great. Yeah, so thanks for the introduction and for those 5 questions. So what I'm going to talk about here today is some of our recent work on understanding or improving our understanding and management of the risk that arises from operating electric power systems and electric grids in regions with high wildfire risk. And so before I jump into this this topic, I just wanted to acknowledge my collaborators in this work, which this is based on a paper which was co-authored with Noah Rhodes, a PhD student in my group here at UW-Madison, and our collaborator Luis Taimo at Texas A&M. So we are the team behind this work. I got a nice introduction to my name here, so people tend to be a little confused about my name being Line, which can easily be misunderstood as Line. So I also like to introduce myself as Line Roald, also known as Power Line. So Power Line as opposed to the power lines that I'm going to talk about more. All right, so that was just to kind of ease into this topic, which is relatively not a relatively sad topic on the impact of electric power grids and how they start wildfires. So that is what we're going to talk about here now. Particularly, as I said, we are going to discuss how to reduce the risk of wildfire ignitions from electric power grids. And so let me first sort of just recap for those of you, many of you probably are aware of this, that there is a lot of fires that are happening, and many of you have probably followed the news and seen that we have had very severe wildfire seasons in recent years. And one of the sources of ignitions for these wildfires is electric power grids. Here are some examples. On the slide, I have a few examples of wildfires that have been ignited by electric power grids. So maybe one of the most severe ones and the ones that have received the most press and people are most aware of is the Camp Fire that happened in 2018 and burnt. It was started by an electric power line operated by and owned by Pacific Gas and Electric, and then quickly burned through the town of Paradise after the fire was ignited. So within 4 hours, this fire burned more than 10,000, I mean, I think it was closer to 14,000 homes and killed 85 people. So this campfire was one of the deadliest and most devastating and costly fires in modern history, and in modern US history. However, this is not the only fire. Since the campfire, there has been multiple other fires in California. There was also multiple fires before the campfire. Also, California, this is not only happening in California, it's also happening across the world. And for example, in Australia, they've had very severe fires being ignited by electric power lines. And particularly, if we can look to the Black Saturday fires of 2009, where some of the most deadly such fires were also, again, ignited by electric power lines. So this is happening. There is a lot of wildfires that are being caused by electric power lines throughout the world. But you might ask yourself, when you look at the power line out there, normally it doesn't seem to be anything about that power line that seem particularly, prone to cause a fire. So I wanted to sort of take us on a little tour through how does actually a power line start a fire. And so what we know is that power lines are typically operated at high voltages. And so when you have a very high voltage line, and there's a big difference in the potential between the line and the ground, then you can get what we call flashovers. So you can see it here. So this is a flashover or an arc. And so this is sort of this lightning strike-like effect that happens when there is a connection between the line and the ground. And so we call this a breakdown of the air, or an arc, or also a flashover. And essentially, what happens here is that even though you may be here in this case, it could be that this tree came close to this line, and then there was a connection between sort of nearby the line and the tree. And so then actually you get the breakdown of the air, and there is current flowing through the air that then can hit the tree, or also, as in this case, kind of go all the way down to the ground. And so essentially, this has the same effect as a lightning strike. And you might have seen this. Maybe some of you have lighters at home that are also electric, that you can use to also ignite candles. And so essentially, this is it's a very similar effect that can happen between a power line and the ground when there is a fault that is happening on this line. Another thing that can happen is that the power line, there's a tree that falls over and onto the line, which causes the line to fall down to the ground. And then you can see here, this is an example. This is from a test done at Texas A&M, where they were also looking at you can see what happens when you down this power line, and you can see that there's a lot of sparks that are coming out from the line, and it's not very hard to imagine that these sparks can also be the cause of a fire ignition. So essentially, these type of things, what is kind of a common thread here is that these things happen when there's something that goes wrong with the electric power line. So under normal operation, there shouldn't be any fires caused by a line. But if there is an abnormal operating condition, it could be that there's either a tree that comes close to the line. It could be that one of the components on the transmission tower are maybe failing. And that can cause this lightning strike or spark kind of events. So here is an example of a fire that was ignited by sort of contact between power lines and vegetation. So here you can see there's a branch here from a tree that has fallen onto a power line and is hanging down. And essentially, this is at the location where the Getty fire was started in October 2019. And so essentially, the Los Angeles Fire Department determined that this Getty fire was caused by this fallen tree branch. And this was a very big fire that impacted the area around LA, and was named for its proximity to the Getty Center. So just this big art museum nearby LA. And so actually, I have a video here, and so let's see if I can make this work. So let me just stop share here so I can share the right screen with you. So here you can see, so this is again from the Getty fire. And this is from a dash cam of a car that is driving on the highway underneath where the fire was ignited. And so if you watch this for a second here, we see that the car is driving, and you can see that there is this lightning strike effect that is happening over here. And so you can see, okay, so here, let's see again, you see it, a little too far. You see that here there is this kind of connection. What is happening here is that this branch is creating this connection between a high voltage line and the ground, and you get this lightning strike effect. And you can see it even in the darkness of the night, that this is this big flash, big release of current and heat into this little area. Okay, so let me just bring us back to my slides here. All right. So is this working? Can I just see, is this, well, can you see my slides again now? Is this working well?
Not yet. We see Lena Roald has started screen sharing. So if you want to put your slides back up, that might help.
Oh, I see. Okay, sorry. Yeah, I will just sort of, I'll have to just restart it here. Thank you for that. Sorry. It's,
well, thanks for asking.
Yeah, I don't want to, I don't want to believe I am making, sharing my screen when I'm not. All right, so I think there you go. Now you can see it. Hopefully.
That's right there. Thank you.
All right, great. All right, so this was just to say, sort of, this is how, you know, you can see also the road on the picture over here, and you know, this was sort of a picture as we saw on this video, which shows this lightning strike effect where the power line is causing the fire. Now we can also ask ourselves, is this a California problem? So actually, I wanted to bring in an example from Madison, Wisconsin here. So this is me. This is a picture I took myself as I was out on a walk on April 7 in 2021, so just about a month ago. And I was walking along the street when I suddenly realized that there's something that is making this like buzzing noise. And essentially, I looked up and I see that there is this branch that is hanging between the power lines here. So you can see there's this branch has, again, similar to the one over here, the branch here in Madison also has gotten caught between a phase conductor and is then hanging down and is touching the neutral conductor, which represents a ground contact. So here there's a short circuit current that is flowing through this branch and it's causing it to sometimes make contact and cause a little bit of a current going through. Now, in this case, the contact was not strong enough to actually cause a sustained current, meaning that, first of all, there was no protection system. This line was continuing to operate. There was no protection system that took the line out of operation, which is what should normally happen. Furthermore, because this was probably a relatively high impedance contact between these two conductors, you know, there wasn't actually any ignition on this branch. But I want to note that this is something that happens because when we look at the power lines that we have, and particularly, you know, if we look around in our streets here in Madison, we all like our trees. And so because we have these trees and we don't want to cut them down and we want to have both trees and power lines because we like both trees and electricity, we can end up in situations where we do get these kind of situations where we have branches that connect these different, that connect and causes these fault conditions. And I just wanted to say here that I took this picture on April 7th. And although we typically maybe don't think of Wisconsin as a place where we do have a lot of wildfires, actually Governor Evers declared a state of emergency just a couple of days before this incident because there had been an unusually high wildfire activity, or we've had already a pretty rough wildfire season here in Wisconsin. So although, you know, there is also these type of situations can be a concern also not only in California, but also across in different parts of the United States and parts of the world. And in particular, this is important to know because ignition events are actually not that uncommon. So, for example, PG&E itself reported more than 400 ignition events just between 2015 and 2017. And in Texas, there's an estimated 1,000 fires that are ignited by power lines every year. And they've also had severe fires that are ignited. And even in my home country, in Norway, which is also not a place we usually think of when we think of wildfires, there has been significant incidents in the past where trees came too close to power lines and also caused wildfire ignitions. So this is a widespread problem. It is not only in California that it happens, but in California, there's a couple of things that make this maybe a little more severe than many other places. And in particular, one of the things that happens in California is that there tends to be very strong winds. And so essentially, when we have very high winds, we have a higher probability that you get a branch that gets blown off the tree and hits the power line. And because you have a higher probability of these branches being blown onto the power line, you also have a higher probability of having an ignition. But then if you do have an ignition, a wildfire ignition in a situation where there is a very high wind, you also actually get a higher probability of large fires. So this fire can then spread more rapidly, grow big, and become harder to contain and harder to fight. And so these are kind of important reasons why it is can be particularly challenging to deal with wildfire ignitions from electric power lines. And I have added in a figure over here, which shows some wildfire statistics from San Diego County. And so essentially here, this shows both, it shows the number of fires and the area burnt by those fires. And what you can see here is that there is less than 5% of all the fires that were started in San Diego County were started by power lines, but those fires actually accounted for more than 25% of the area burned. So what we observe here is that fires ignited by power lines tends to be larger than other fires, and this is because of this wind, wind being both a reason for them being more likely to happen, but also because when there's high wind conditions, the fire tend to grow large. Another thing that is also important to know is that the wildfire risk is increasing. So as we are looking towards the future and effect of climate change will become more apparent, we are actually probably going to see an increase in the number of days with high wildfire potential in many different parts of the world and also across the country. So this figure over here sort of shows just a map in the increase of the number of days with high wildfire potential on public lands. So that is why there are just certain parts here that are colored. But when you look at this, you can see that sort of throughout there is going to be an increased number of days with high wildfire potential and high risk of fires. Although some regions are maybe more impacted than others. All right. So let me also just take one step back here and think about what is it that we are trying to do in order to prevent those fires from being ignited, because that was what I promised you to talk about. And so I'm going to use here and sort of put out a little bit of a timeline here for fires caused by electric power lines in California. And so there has been many fires in the past, but I'm going to use the example and the events that have happened after the Camp Fire in 2018 as sort of as a starting point. So you can think about above here, there's already also been a number of fires that were started earlier. But so in November 2018, there was this transmission line that was operated by the Pacific Gas and Electric, which caused this Camp Fire. And so this happened around here in this area. And then just within a few hours, this fire spread very rapidly and burned through the town of Paradise. And then essentially and ended up killing 85 people and burnt more than 13,000 homes. So as a result of this fire and financial liabilities and proceedings due to other fires in the past, PG&E itself filed for bankruptcy protection in January 2019. And then in December 2019, PG&E agrees to pay $13.5 billion to the wildfire victims. So you can imagine this is a huge sum for any company to have to pay. And then just a little later in June 2020, PG&E pledges guilty to 84 counts of involuntary manslaughter. So they are saying, we are taking responsibility for this. We are going to pay for the damages, and we are also taking responsibility for the fact that were people dying during this event. So you can imagine that this is obviously very sad and very bad for the company, very sad for everyone in the area which was burnt. And so there's this, and this really raises this question of what can we do to prevent this from happening in the future? And so, we start around in early 2019. There's an increased push for PG&E and the other utilities in California to provide plans for how to mitigate this wildfire risk. And so they put out some plans to also to try and mitigate the impacts of these severe wildfire risk events. And so I have actually gotten the timeline a little wrong here. This should say 2019, not 2020. But essentially in October 2019, so essentially between after they have filed for bankruptcy and before they make this settlement, PG&E initiates what is called public safety power shutoffs. So essentially you can imagine about a year after the campfire, the PG&E takes this step that they say we are going to shut down parts of the grid in order to prevent any such wildfire ignitions to happen again. And so this was already agreed on. It was said that this is going to happen. It was written about, they had clarified with the California Public Utility Commission. And I remember reading these documents that summer before it happened and thinking like, wow, this is, it's pretty big for an electric company to sort of make all of these, say we are going to shut down power to people. That's typically not what they want to do, because after all, they are making their money by selling power. And so they essentially start a public safety power shutoff on October 8th or October 9th in 2019. And this public safety power shutoff disconnects electric service for 3 million people. And this is the moment where we should stop and we say, and we say 3 million people, or which is kind of approximate the same as 1 million customers. And this is where we stop and we say, just wait a second, like 1 million customers or 3 million people, that is a lot of people who are losing power, who has to be without power for days in order to prevent those wildfire ignitions. And so this really also causes this sense of like what's happening here, people got very angry with PG&E for turning off their power. So you really get stuck in this very challenging trade-off between trying to protect people from wildfire ignitions, but also trying to serve power to them so that they don't have to live through a power outage. And so in this like very challenging trade-off between having wanting to prevent wildfire ignitions and wanting to continue to serve electric power, this trade-off is what we are particularly interested in our research here. And so in order to explore this a little bit more, I will now discuss some of our modeling and mitigation strategies, strategies for modeling and mitigating wildfire risk. So this is kind of our thinking about this topic. So the way I think about, one way we can think about wildfire risk is that the wildfire risk is essentially a combination of the probability of having an ignition times the size and intensity of the resulting fires times the damage caused by that fire. And so if we look at this equation, we can say that utilities mostly control this one aspect. So utilities mostly are able to try and reduce the probability of having an ignition. And once the fire is burning, there's, both it can be very hard to fight the fire in general and very expensive, but also the utilities typically are not the firefighting organizations. They might collaborate with organizations that are fighting fires, but they themselves are not in control of that. And also they cannot control where this fire is going to burn through. So really where they have to focus their effort is in order to try and prevent this ignition from happening in the first place. And this is actually quite different from a lot of other type of wildfire mitigation, because traditionally, if you think about wildfire, like firefighting, for example, if you are a organization dealing with firefighting, you are mostly concerned with how to kind of reduce this part of the equation, right? And how to prevent the fire from growing large, and how to minimize the damage that is caused by the fire. Because as a firefighting entity, these organizations that fight fires, they typically don't control where those fires are being ignited. So here it's like sort of a little bit turned around, and this is why we need to think about it in maybe a slightly different ways than what has been happening before. So in order to try and reduce this probability of starting a fire, there are several risk reduction strategies that a utility can use. So they can do infrastructure upgrades. So for example, undergrounding of lines, or they can do vegetation management where they are going out and cutting down the trees around the lines. Or they could just start doing more frequent maintenance. So making sure that all of the lines are in good condition and that nothing is breaking. And so all of these is kind of things that are very good to do. They mitigate wildfire risk, and they also overall improve reliability. So if I'm an electric power customer, these things are going to improve my reliability, not only in situations with wildfire risk, but also in all other parts of the year. The problem here is that these are really long-term solutions because they require both investment and time for implementation. So, this is not something I can do for tomorrow. If I see that there's a lot of wind coming and I'm having a high wildfire risk for tomorrow, it's kind of too late to go out and upgrade my infrastructure, do vegetation management, and implement more frequent maintenance. I have to plan this ahead of time. So the type of scenario that we were particularly interested in was this like shorter term operational perspective. And so in the short term, these utilities, they have much fewer options that they can use in order to try and reduce the probability of ignitions. So they are doing some changes to the protection systems of their lines, which is related to what we call automatic reclosing, which is essentially saying that, if a line experiences one of these like lightning strike type events, an arc or a fault, what typically happens is that the recloser will open, or there's a circuit breaker that opens so that there is not so much current flowing. And then so they essentially take out the faulted part, they turn off that line. And then sometimes what happens is that, you just try and close it back again. Because in many situations, the fault will have disappeared. If it was a tree branch, for example, when you close the line again, that tree branch might already have fallen to the ground. However, if it hasn't, and maybe that tree branch is now experiencing a second such lightning strike type event, then that could contribute to having a higher wildfire risk. So they might, so utilities, one of the things that they do is that they disable this automatic reclosing of the lines. Another thing that they do, which is a much more disruptive measure, is public safety power shutoffs. And the benefit of public safety power shutoffs is that you say, I'm going to turn off this line, I'm going to shut off this line, and because there is not going to be any current flowing on this line, even if I have a fault, even if there's a tree falling onto my line, or there's a tree branch that blows into it, or there's some other kind of wind-related damage to it, which means that it falls to the ground, regardless of what of these things happen to the line, that would be bad to the line and I have to go and fix it. But at least I'm not going to have one of these lightning strike type events. So I'm not going to get that ignition lightning strike thing happening. And so that is great, like that really reduces the wildfire risk by a lot if I shut down the power line. And it's also really fast to implement. So these are kind of the main benefits of this approach, and this is why it is being used. So essentially, I just turn off a line. I have no wildfire risk arising from that line whatsoever. However, if I turn off the line, I also cannot send electricity to the customers through that line, meaning that people are losing access to power and they are experiencing these large-scale power outages that I was describing just before. So although these short-term solutions here, they really have this trade-off where they might be effective in mitigating wildfire risk, they can be fast to implement, but they really reduce electric reliability. People lose access to electricity at points in time where maybe they really need it because they might have to evacuate if there is a fire being ignited nearby from other sources than the electric grid. So here again, just coming back to this public safety power shutoff that happened in October 2019. So, approximately 100 million customers lost power, that where I said, hey, wait a second, that's a really large number. So you can then ask your question, like, was that worth it? And so when they shut down a lot of these power lines, many such power lines across the San Francisco Bay Area, in different parts of California, and before they turn those lines back on again, they send out a crew and they go and inspect the line and they check if there has been any damage, if there have been any trees fallen over, or if there are any tree branches that were blown onto the lines, or any lines that fell down. And when they went and they did those inspections, they did find that there was about 100 potential wildfire ignitions and 100 potential wildfires, essentially, that were avoided. And so you can imagine, now you can start asking yourself, what is this trade-off that we're looking at here? There's 1 million customer losing power, a potential 100 wildfires that were avoided. Was it worth it? Like, these are kind of questions that are really, really hard to answer when you start asking them. I think it's also worthwhile to note that although 100 wildfires were avoided, or 100 potential wildfires were avoided, not all wildfires were avoided. And in particular, there was the Kincaid fire in Sonoma County. This was sparked by a high voltage line in an area where the distribution system was shut down. So essentially, the PG&E had said that, let's shut down the distribution grid, but let's keep the high voltage transmission grid going because those lines are less risky. So as we're talking about these like high voltage and lower voltage lines, I also just wanted to you can start asking these questions because, 100 wildfire ignitions were avoided by shutting some lines down. But then there was another line that caused an ignition. And this kind of really also begs this question of which lines should be turned off. So maybe to kind of look a little bit more at this Kincaid fire case, we can also look into, what is the difference between a high voltage line and a lower voltage line. And so I have kind of put up a picture here of transmission and distribution lines. And so power lines, when you are looking around here in Wisconsin or anywhere, I mean, whenever I go on a road trip, I always look at the power lines along the road. And so you see that there's a large range of different kinds of power lines. And so you have some transmission towers that have really, really high voltage lines that can go all the way up to, several hundreds kilowatts. And then you have multiple steps where you have this would be very high voltage transmission, long distance transmission of electricity on these large towers over here. And then you have kind of different, more regional transmission of electricity in these slightly smaller towers over here. And then you can go all the way down to also more regional. This is also still more regional and within a smaller region. But then you can go all the way down and you continue getting smaller and smaller and smaller towers until you get to the point where you are right nearby your house. And essentially, what you can see here is that there are a few reasons why in terms of wildfire ignitions, these different types of towers have different levels of risk. So these large transmission towers, they are for long distance transmission of electricity. They're more dangerous because they have a higher voltage, but they also have there are much fewer towers and components associated with them. So every tower, there's maybe 100 meters between the towers. So you can have really few towers, as you see here. You can get really, really far by just having a few towers along the way. And then you can also see on this picture over here that the area around those very high voltage lines, it is also being cleared out. So you can see that there's this road essentially that goes along, or this cleared out area, or large right of way where there are no trees nearby this line. And both the fact that there are fewer trees and there are fewer components contribute to the fact that there is actually a smaller chance that there will be a wildfire ignition caused by this line here, if I think about it as a wildfire ignition probability per kilometer line. Whereas if I look at the more local distribution of electricity, where I have many towers, they are spaced out much closer to each other. There's much more transformers. There's just a lot more components that have to function correctly. And also there's a very much smaller right of way, like these lines, they can essentially go straight through a wood or essentially through the trees. And all of that contributes to there being a much larger risk of a flashover or essentially and then causing a wildfire ignition. So essentially what we know from statistics from PG&E is that per kilometer of line, there's a 3 times higher chance that a distribution line is going to cause an ignition than a high voltage transmission line. And there's also a lot more of these lines, and they serve a lot fewer people. Because if there is one distribution line, typically, goes to maybe serves one neighborhood or maybe just a street. Whereas these long distance transmission lines, they might be important to serve electricity to large cities. So essentially, it's also from the perspective of who are you cutting power to, it is also easier to turn off these distribution lines than it is to turn off these transmission lines. However, keeping them in operation also means that there is still a remaining risk, as we saw in this Kincaid fire example. Okay. So if you now go back and we ask ourselves, which lines is it that should be turned off? We can look to PG&E and other utilities, and we can look at what are their criteria for designing that. And essentially what they are looking at is questions such as if you have outage producing winds, or you have vegetation that is very prone to fire. So essentially, if you have a high wind, you have this higher probability of having an outage. If you have an area which is very dry and has a lot of vegetation that has dried out, that would cause this fire potential index to be higher. And so now you can combine these 2 factors, winds that can increase the probability of ignitions with a fire potential index that also take into account wind, but also vegetation. And you can combine it, and you can think about now in different areas that you can evaluate what is the risk of wildfire ignitions. And so what appears to be happening, sort of based on what we are able to read. I mean, we don't work directly with PG&E, and so we don't know exactly what's going on there on the inside. But what appears to be happening, sort of based on what we are reading in their documentation of it, is that they essentially have something like a risk threshold, and they say that if the wildfire risk associated with the line is larger than some threshold R max here, RL max, then we are going to shut the line down. So I'm just going to use this kind of threshold here. RL is going to represent the risk associated with the line, and RL max is going to be the threshold that I'm willing to use. And so our question was then, of course, can we do better? Because what happens here is that if I'm turning off my lines only by considering this risk threshold based on the wildfire risk alone, then I haven't really accounted for this fact. How much power am I going to shed? Like, how many people are going to lose access to power if I turn off a specific transmission line? And so that is what inspired us to formulate this as an optimization problem, which we call the optimal power shutoff. I just also want to take a step back here and say we don't think any power shutoff is optimal. The optimal power shutoff is no power shutoff. But in the case of wildfire risk, the question that we're trying to ask is, can we create a more optimal power shutoff than what has been done in the past? And so we formulate this as an optimization problem. And so in an optimization problem, the first thing that you try to decide is that you want to say, what is our goal? What is our objective function? What is it that we are optimizing for here? And essentially here we have this objective function that has 2 terms. The first term here is saying we want to maximize the amount of load that we are able to deliver to our customers. So essentially, how much electricity can we serve to customers? And this is sort of essentially expressed as a weighted sum of the amount of electricity demand at each node in our network. So you can imagine this as being every city in California would represent a certain demand for electricity. And then we say that we are able to shed or kind of shed part of that load, so we can turn off the power to a fraction of each of those loads. So we can say, for example, half a city is going to get electricity, the other half is not going to get it, or so on. The second term in this objective function is that we want to minimize wildfire risk. So we are trying to, so our wildfire risk here is essentially expressed as the sum of each of the risk, wildfire risk associated with each component. So that is similar to what I was describing before with this RL max. But here I have, again, evaluated it for all of the different parts of the electric grid. And then I have some what we call decision variables here, where I can decide whether or not I'm going to turn off these lines. And so essentially the trade-off that I'm looking at here is essentially I'm trying to say I want to maximize the amount of electricity I deliver, and I want to minimize wildfire risk. And the reason I cannot shut down just everything here and have a zero wildfire risk, and then at the same time say I'm going to serve all of the load, is because that wouldn't physically work in the electric power system, because we need to have those transmission lines working and operating for it to be possible to serve this demand. And so we are going to also include that in our problem here, just a little model of like how the electric system works. But before I get there, I also want to say that there's another parameter in this function over here, which is this parameter called alpha. And this alpha is essentially a parameter that determines our trade-off between load delivery and wildfire risk mitigation. And so essentially, if I set alpha is equal to 1, then this term over here becomes 0, meaning that I don't care about how much load I'm serving. I don't care about serving electricity to customers, and I only care about reducing the wildfire risk. If I set alpha to 0, then I say I don't care about the wildfire risk. I'm only caring about sending electricity to my customers. But by varying alpha between 0 and 1, we can actually kind of trace out a trade-off curve between how much electricity we can serve to people and how much wildfire risk reduction we can achieve. Okay, so I'm not going to go through this in all too much detail here, but I'm just going to say that when we do this kind of a formulation, we end at a problem formulation that looks like this, which we call the optimal power shutoff problem. So here you recognize our objective function, you recognize our expression for the total load served and the wildfire risk here. And then we have a bunch of other equations over here that essentially helps us model how the power system is operating. Because an electric grid, for example, has to satisfy power balance, it has to satisfy power flow constraints, it has to satisfy generation constraints, and it also has to, I can't turn off a substation or a node in my system and then have the lines that are connected to that node operating. So that is something that is captured here in these component relationships. So essentially, you can just think of all of these constraints as being constraints that represent how we operate the power system. And this operation of the power system is what ensures that if we shut down a component, that reflects the impact that has on how much electricity we can serve to customers. All right. So this optimization problem here, this is an optimization problem. We call it a mixed integer linear program. We have some of our variables here are integer variables, so they are 0 or 1. We have another set of variables that are continuous variables that can vary continuously in a range. And if you are familiar with optimization, you would know that a problem that includes such integer variables that are either 0 or 1, those are called combinatorial problems or discrete problems or mixed integer problems. And they are actually quite a lot harder to solve. However, in the formulation that we're having here, we can use what we call an optimization solver and just take this whole problem formulation and put it into that solver. And the solver is going to tell us, how do I have to schedule my generation? How do I have to operate this whole power system in order to serve as much load as possible while minimizing wildfire risk? And very importantly, it's also going to tell us which of the transmission lines and generators and loads is it that we have to turn off in order to avoid wildfire ignitions. So that is our formulation of our problem. I wanted to show you some results. So this is a very small little case study, but it's more for illustrative purposes. But we are currently working on putting together a case study that reflects much more the realistic grid in California. So our test case is here. This is a standard little test case from IEEE called the IEEE RTS GMLC. The interesting part about this test case is that it is located in California. So we have geographical coordinates associated with it. And you can see here on this map what it looks like. So this is the coast of California over here. You can see that they're part of this grid that is in Southern California, and we have some parts of it that stretches over into Nevada and Arizona as well. And you can see, so what we have done here is that we took this little grid test case, we put it onto the California map, and then we overlaid it with a wildfire risk map that is representative of the October 2019 wildfire risk in California. So all the yellow parts, the white parts here are areas where there is low risk, light yellow part means medium risk, dark yellow is high risk, and then these orange parts are regions with very high risk. And so then we take this, we estimate the risk of each of our devices based on the location. So for example, this transmission line here, so I should also say this, the different nodes here represents the different loads and cities that we are trying to serve electricity to. And each of the green lines here represent the transmission line. And so essentially here, what we do is that we look at, for example, this transmission line that goes through this area over here from one node here to another node over there. And we calculate the risk associated with this line as the kind of cumulative risk along the whole length of the line. And then we also make some adjustments based on the voltage level. So as I said, if you have a transmission line, we have a lower risk than if you have a distribution line. And so let's look at some results here. Like what happens if you take this model that we have, you put it on top of this California test case, and what is it that happens to California in this case? And so we start out just looking at our original grid, which is a high risk case. So our risk here is just, it doesn't have any units, so you just have to believe me that this is a risk number. Our risk number here is 746.2, which is high. And the total amount of load that we are serving in this test case is 8,550 megawatts. So then we are going to our optimization problem, and we are doing this thing where we are trying to maximize the load while minimizing wildfire risk. And we are going to start out and look at a case here where we are just setting this alpha to be 0.01. So this is still a small value, but as we'll see, it actually has a large impact. So the results, if I solve my optimization problem and I look at what comes out of there, I get this schedule for which of the power lines I should be turning off. And you can again see this is the same network. It looks a little bit different, but essentially everything that is in green here are transmission lines and nodes that are operating. The blue dots here represent generators in this network, and the red part is where I am shedding load. And you can also see that some of the lines are grayed out, meaning that they are also turned off. And so you can see that, not surprisingly, in these areas where there's relatively high risk, there are many of the lines that are turned off, and some places where we have to shed some load. And in particular, you can see that actually we are able to here in this case, although we chose this very small value of alpha, we actually reduced the total wildfire risk in this case by 57% relative to the other case. And our loads, we are only shedding 0.1% of the load. So here you can see we get a really, really big wildfire risk reduction while having very small reduction in the risk. And then we can also do an even lower risk case where we are now choosing a higher alpha. So in this case, we are saying, okay, I'm going to weight more. I'm more interested in reducing the wildfire risk here than I am in serving the load. So I'm going to push more in that direction. And essentially what you see here is that in this case, I am turning off a lot more of the lines. You can see all these red dots over here. They represent now that there are many areas where power has been shut off. And these are places where, there is high wildfire risk in this region. And so people, there's too high risk to keep the electric grid going. And you can also see that there are other parts of the grid over here where we have load shed. But essentially what this means is that we are able to reduce the risk by 92% relative to our base case. And this happens while we are also shedding 15% of our load. So this is just saying also, you can see you can get different solutions here depending on how much you want to weigh continuing to send power to people versus how much you want to reduce wildfire risk. I also just wanted to highlight here that we talk a lot in terms of when there's discussions about wildfire risk and mitigating wildfire risk and doing these power shutoffs. One of the main things that one can do is also to introduce a distributed generation. So essentially solar PVs, or maybe use of electric vehicles in a smart way, or also have just local diesel generators. And this can help. And what we see here is that there are certain parts of the grid that are disconnected from the main grid, but they are keeping operated because they still have a lot of different generators, distributed generators that are attached. Okay. And so the next thing that I'm going to look at is just like, how does this compare? You know, I told you before that if you look at sort of how things are being done today, it is using this risk-based threshold and just saying, like, if a line has a risk that is higher than a certain threshold, we are going to shut down that line. And as just to recap, what that meant is that if we use this risk threshold, we are only measuring the wildfire risk, but we are not taking into account what the resulting impact on electricity delivery is. So meaning that we don't care about how many people are losing access to power. And our comparison here, so what we are going to do is that we are going to compare the wildfire risk levels and the total amount of electricity or load that we are able to deliver obtained with this current practice and with our optimal power shutoff. And for both of those methods, there is a design parameter that we have to choose. In this current practice, where we are just using this wildfire risk threshold, we have to choose that threshold. In our method, we have to choose that trade-off parameter alpha. And so what I'm going to do is that I'm going to use these two, I'm going to vary those parameters, both this threshold and this alpha, and then I'm going to look at what are the different trade-offs that I can get between wildfire risk and power delivery. And so essentially, we are going to look at this graphic over here. So you see here on the y-axis, if I go higher up here, I get a higher wildfire risk. On the x-axis, I'm looking at a higher load delivery. So as I move from left to right here, I increase the amount of electricity that I'm able to deliver. And essentially, what this comes down to is that I really want to be over here in the corner. So over here in the corner, I am serving a lot of electricity to my customers, and I'm having a very low wildfire risk. So what I'm going to do is that I'm going to use this current practice method and our optimal power shutoff, and they're in orange and blue respectively. And then we are going to evaluate these different solutions that we get in terms of higher wildfire risk or low delivery. And I'm going to plot the results on this map. And we are going to see a Pareto trade-off curve on this map. All right. So this is what the results look like. And so you can see here that all these orange dots, they are solutions that correspond to the current practice, where we're only accounting for the wildfire risk. Whereas in our optimal power shutoff method, we are getting these blue dots that you see over here. And essentially, one thing that is important to note here is that with the optimized power shutoffs and using optimization, where we are taking into account both the amount of wildfire risk and the amount of load delivery that we are able to achieve, we are actually achieving lower risk and smaller outages across the board. So regardless of which parameter value that I choose, I'm always doing better. You see this blue, all the blue dots are closer to the corner over here than the corresponding red dots, meaning that for the same level of load I can achieve the same level of load delivery at a lower wildfire risk. Or conversely, I can achieve, for a given wildfire risk, I can achieve a higher load delivery with our method. So this is just saying that taking more information into account is going to give you a better solution. I also think it's interesting here to look at why this is possible. So why do we actually end up getting solutions that are better? And in order to understand this, we are just going to look at these solutions in a little more detail. So first, I'm just going to look at the solution that we got from this current practice based on just a threshold value. And essentially, if I go and I'm going to look at a different graph, so this is a little different than what was there on the last slide. Here, I am looking on the y-axis, I have the power transfer, so the amount of power that is being transmitted across a transmission line. So essentially here, in this case, for example, from this node to this node, the amount of power that I send across here. And so that is what I'm plotting here on the y-axis. And then on the x-axis here, we are seeing a higher risk. So essentially, this is the risk not for the whole system, but for the individual transmission lines. And essentially, if I look at my current practice based on this threshold, I haven't actually plotted the values in this graphic, but essentially what this threshold method does is that it says that I'm going to choose just a given threshold. Any line that is below that threshold, I'm going to keep it in operation. And any line that is above that threshold has a higher risk than that threshold, I'm going to shut it off. And so essentially, I'm prioritizing keeping this transmission line on just simply based on how high their risk is. And the result that we get is that we are shutting off all the high risk lines and we are keeping all the low risk lines in operation. Now I can also do the same thing, and I can compare the risk and the power delivery and the power transfer for the optimized power, the solution of the optimized power shutoff problem. And so what you see here is that I have actually plotted for each of the lines on this map. I have plotted what is the amount of power that is flowing across them, and what is the risk value associated with them. And so essentially, for each of these lines that are grayed out, the power transfer is 0 because they are inactive, they are turned off. And so you can see that these lines that are turned off, they all appear down here along the x-axis here. And you can see that there are many of these lines that have a high risk that have been shut off. Now, we can also look at the lines that are still in operation. And so we see that there are more lines that are in operation here than what was there before, or there is less load shed than what we saw on the previous slide. And what we see here is that there are many lines that are active still. And the important part to notice here is that most of the lines that are active are still very low risk. So they have a higher power, they have a high power transfer, and most of them are in low risk. So essentially what we see here is that our methods turns off most of the lines that are in this high risk category. However, our method also keeps a few of these like high risk but high power transfer lines in operation, and then instead it shuts down many of these lines that have a low risk. So essentially what this method is saying that, many of these lines, they are not important for power transfer. They aren't important to transport power across the grid, but they still have a non-zero risk of starting a fire. And so what I'm going to do is that I'm going to shut off those lines because I don't really need them. And then instead, I'm going to keep a couple of high-risk lines in operation because those lines are really important if I want to continue to keep power on for as many people as possible. And so essentially, by prioritizing based on both the risk and the power transfer, we get this kind of picture. So instead of having this sort of sharp cutoff here, where some are kept in operation, some are shut off, we get this sort of more kind of blurred line where some lines are kept on, although they are high risk, and then many lines are shut down, although they are relatively low risk. Okay. So essentially here, I just wanted to, so this is, I'm going to conclude the presentation here now, but essentially what I just presented is a first method for optimizing public safety power shutoffs, which considers both load delivery and wildfire risk. We have seen that this method really performs kind of consistently better than what is current practice. And the reason it is able to do so is that it's keeping some high-risk lines in operation to keep the lights on for more customers. So this is really just the first step in the direction of trying to understand these trade-offs better. So this is based on a paper that recently came out. But there are very many questions that remain to be answered here. And so, for example, so one question is, what is the right trade-off between wildfire risk and power outages? How much wildfire risk are we willing to take before we say the power should be shut off? You can also start asking questions about who is being impacted by wildfires and who are being impacted by power outages. And, are these the same people? How is these impacts being distributed across the populations? Are there certain part of a grid where the impacts are more severe than others? And generally, just in order to sort of understand all of this, the things that we are working on these days is really trying to better understand the risk modeling and also develop better methods to assess this risk so that we can support utilities and policymakers in making these decisions and trying to answer those questions. So that really takes me to the end of the presentation here. I put in a little slide here just to say, we do have code that also can be used in order to run this type of methods that is publicly and freely available. This is open source code that can be downloaded on GitHub. And with that, I think that was my presentation.
Thank you very much. Bia, would you like to read the first question in the chat? And then other folks, if you want to, you can also ask questions by typing in the chat, or if you'd like to unmute and to start your video, you can also ask questions that way. Bia.
Yeah, so Raj asked a question. He says, can drones be used to continuously the entire power network and use predictive algorithm when weather forecast indicated potential for a wildfire condition and power can be shut off, intelligently and switch to battery power on the distribution end? Also, use of microgrids will make it more localized. And that's the very first one in the chat.
Yeah, so great. Yeah, good question. So I think that, yeah, so that there has been a lot of work recently, and I mean, there's a lot of movement going into trying to improve. Yeah, I mean, for example, using drones both for maintenance and inspections, and kind of checking in on those lines and checking, are there trees that are growing very close by, and you can also imagine that using drones to inspect the lines after you are done with the power shutoff could really significantly speed up the process of getting things back online again. So definitely, I mean, that is, I think it's already, these are things that are, I'm not exactly sure how far along that is, but definitely these are things that are being considered and I would believe will become are already important and will become more important in the future. So definitely that is an important part of this, is trying to do more inspections, be more proactive about maintaining the system well, so that you have a smaller chance of having this risk. And I think that is also something I tried to say something around that here in the beginning. If I just let me jump here, that is that there is this trade-off between having long-term and short-term solutions, and so improving. There are a lot of these things that are happening here. These infrastructure upgrade, better vegetation management, better maintenance, definitely there are super important solutions in order to handle this problem better in the future. In terms of the questions about microgrids and sort of distributed operation, battery systems, and so on, so that is also what I alluded to over here on this slide, talking about, what if I shut down the line that goes to a certain node in the network? I might be able to keep the electricity on to customers in that area if I have sufficient distributed generation available, like a microgrid or a battery powered diesel generator, solar PV, and so on. So that is also something that is an important question to ask, and this is actually being installed in parts of California. PG&E has several such microgrids sort of getting set up in order to at least maintain some power to areas where there might be frequent power shutoffs.
Yeah, do you want to ask the DC question?
Yeah, so he also says, does high voltage DC transmission pose less risk than AC power line?
Yeah, so that is an excellent question. Does it not? So you still have the same problem that you do if you do get something that if you do get the connection between the DC line and the ground, you still have very large voltage difference, and you will still have a high current, and you could still get an ignition. I mean, there's one high voltage DC line in California that. So I don't know if that has. I mean, I don't. And I think that this also comes back to this question of how dangerous is a DC line relative to a high voltage AC line, and I don't think there are. I mean, a lot of this also comes down to details of protection systems, how quickly you can turn off a line if you have this lightning strike type event, and you have an arcing event or a fault. And so I'm not super familiar with this. So I will stop it. I will stop it there. Both of them pose a risk, I would say.
And then, are there any questions? Would anyone like to ask a question right now by unmuting and turning on your camera or just unmuting. I want to give people a chance to speak their questions. If not, we'll ask again in a little bit. Bea, do you want to ask Larry Winkler's question there about, yeah.
Yeah, Larry asked, is there a way to brown out areas instead of turn them completely on off?
Yeah, so that is actually, what happens in the problem that we are solving here is that there are certain areas where, maybe there used to be 2 transmission lines coming in, and now you have less transmission capacity. And so you might only be able to serve half of the load. And actually in the slide that we are looking at here, there are certain of these nodes here that are yellow. And so those nodes are, situations where are areas where part of the load is being shed. And part of it is being kept on. And you can imagine this as being sort of a kind of like a rolling blackout type situation where you maybe shut down a neighborhood for a certain time and you turn it back on again, and then you shut down the next, or maybe you turn off power to half a city. So there are ways in which you can do kind of more of this rolling blackout. In terms of brownout, I don't know if that sort of answers the question. I mean, I don't think it's common to sort of lower power quality. Essentially, you probably want to keep power on to people with sort of the level of power quality, essentially the voltages and the frequencies and so on that you need in order for equipment to operate correctly.
There's several more in the chat, but I want to give people a chance to speak a question if you'd like.
Yeah, so I actually also have a question to the audience later if there is a.
Would you like to pose that now? Would you like to pose that question now?
Yeah, so maybe there's time for folks to think about it. So like one of the things that I think is important here that I keep sort of thinking myself is that, I'm a power engineer. I think about this, I comment this from sort of this power perspective, and we are trying to use our technical knowledge about the grid in order to provide better solutions, right? And to say, hey, it's possible to continue to provide power while also reducing wildfire risk more effectively. However, there is, as we look at these curves that I showed over here, this is like a whole range of possible solutions. So you can really ask this question, what is this trade-off? Like, how much do we really want to reduce wildfire risk versus how much do we want to keep power on? And these are, kind of more, these are, and how much do we invest in it? And these are kind of sort of maybe also questions that I sometimes feel that it goes beyond what we power engineers probably should answer. And something that is maybe more a task for a regulator or policymakers to try and think about, like what is the right trade-off? And so, I'd be curious, like, if anyone has any thoughts on, what would your thoughts be? How would you feel if power was shut off to protect you from wildfire ignitions? Would that be okay or not? Right.
Would anyone like to respond? How do you see the math of turning off your power to protect somebody else?
I think we have to first address what is the definition of reliability. Normally, reliability means the customer gets on-demand power at all times. That's a very general definition. And somehow we have to attach a caveat as to reliability in view of natural disasters, or in this case, you can say man-made disasters, as to what reliability means. Do the customers have to sign up for a reliability insurance where they tell the utility, yeah, you can shut my power should there be a fire threat, and some other customer pays a little bit more on their utility bill to say that, no, I need power at all times. So there is a surcharge for people who want to opt in or opt out. So that will be one of my suggestions. And you already talked about the role of regulators. And So by the regulator, if they are very stringent on the utility, many utilities could go bankrupt.
Thank you, Raj. Other folks?
I was just gonna say, just hearing that, I guess like being in Wisconsin, I've never really thought of wildfires being an issue, but if I was like in Australia with the wildfire last year in California, I feel like I'd want to put a lot more into safety for it, because I've never been afraid in Madison that my house would be burned down or anything. But if I was in an area like that, I could definitely see the need for an investment and a little more trade-off.
Right. Yeah. No, it is. These are interesting questions, and I think also what Raj was mentioning, right, about like what is the reliability that we need. There are many different ways in which one can be prepared for emergencies. If you are prepared for like not having power, like for example, here I can say I didn't prepare for it getting dark, so I should probably turn on my light. But you know, like there are different ways in which you know, we prepare ourselves for situations where power is lacking. And I don't know, like you know, in the middle of winter here in Wisconsin, you know, if you lose access to heating, you have to have a plan B somehow to try and heat your house or figure out a way of staying safe, right? And so I think that, you know, these questions are very important. Like, what is the you know, how much are we willing to pay for reliability, and questions also around like what does that mean, and what other ways can we live with? Can we be better prepared to live without electricity for a while? The challenge, I think, from a sort of society-wide perspective is that maybe not everyone has money to pay for electricity, to pay more. There are people who need electricity for medical applications. You know, there's a lot of challenges. I think we have built a lot of our world around having that continuous access to electricity. So what does it mean if we lose it? I think that's
Well, I'm wondering how the increased technology, the better technology for batteries is going to affect us, so that I imagine in 10 years we could all have an affordable battery. Well, many of us could have an affordable battery in our house, so that we'd have enough to last 2 days or 3 days as a reserve. Electricity is not like fuel oil or that you can have, or LP, that you can have a reserve out in your tank. But with batteries, we'd be able to do that. And I wonder if that would change the equation and change the sociological angles. And that's a matter of time and technology coming up.
yeah.
Lawrence also asked, what's the possibility of delivering electricity with underground cabling? I don't know how frequent that is or how possible that is with the kilovolts levels that you're showed with the above ground power wires, but that's a source of.
It's a big question. Like, I mean, it's also similar to, I mean, so we discussed high voltage DC before, right? I mean, DC lines are easier to put on the ground for long distances. With AC lines, there's a limitation on how long you would want that line to be on the ground. I mean, because it changes the characteristics of the line, and you have a lot more. I mean, the electrical characteristics essentially change. Yeah, the lines become capacitive instead of inductive, and so there's a number of questions around that. Like, would that be effective? It is very costly for sure. And then there's also there's also some questions on how do you operate it. My sense would be that you know, that might be something that I hope that whatever we are asking here about public safety power shutoffs are things that we are going to figure out over time, and that this maybe won't be a problem in the future. And so for example, undergrounding of lines, I think, will probably be definitely a part of the equation in some parts maybe of the country or in California. I mean, there are other things to consider also in terms of, you know, California is a place where there's earthquakes. You have to, so there, one just has to make sure that if you do decide to dig something into the ground, that these things also are safe for other kinds of hazards, that you're not over optimizing for one scenario, but also remain, safe for others. So, but I think that undergrounding is probably something we will see. And actually, in fact, in my lab, we are also working on some alternative technologies for using AC transmission at lower frequencies to also do transmission that might be more suitable also for large-scale undergrounding. That's one of the scenarios we are interested in looking at there. So yeah.
Oh. Does anyone have a question they'd like to speak to?
I think that we have a situation developing, at least in this nation, where we want to become more electrified for mitigation of climate change issues, and yet we are faced with issues like California and Texas had with electric power delivery issues. Is there any research going on right now in how to aid that, smooth that transition between needing to have a reliable, relatively large electrical supply so that we are not using fossil fuels?
Yeah, no, this is what we think about, or at least I think about every day. Like, how do we make this happen, and what is it that we can do as researchers to contribute towards that? Yeah, I think it's a very exciting time for the grid. It's a very exciting time for electricity supply. It's exciting because, as Tom was just mentioning, the battery technology is becoming better, more available. If everyone had an electric car, maybe you could use that car in a smart way to also provide, you could use that as a battery that you had available for yourself in case you experience a power shutoff.
So things like that, actually.
Exactly, but then if you have to evacuate, then that becomes a huge issue, right? So
used up your electricity to move that car.
Right. Exactly. You need electricity to move that car. So there's these there's a lot of So there's a lot of different aspects to this. And there has been, there is research on this in terms of, can you use, how could you use your electric car as a battery for yourself? And then, of course, what does that mean, in terms of being able to evacuate if needed? How you can think about, also just what do we need to, how do we need to build out our electric infrastructure in order to support increased load, for example, from electric vehicles? How can we do that in a way that is such that it becomes more reliable, that we take into account all the scenarios that can happen? And so I think, one of the things that we work on is trying to understand how do we develop methods for taking into account rare events. So events like what happened in Texas. We have a research project that is ongoing where we were looking at what is the impact of widespread cold temperatures on the grid. And how does that impact if you have different kinds of generation technology? And of course, it's very interesting when you have a meeting about this one day, and the next day you read the news and you see, oh wow, it's unfolding as of right now, and it tells us just that it's very important that we are very proactive in thinking about and identifying those scenarios and bringing them into the tools that we are using, so that 20 years from now, it doesn't come as a surprise for us that I don't know, there's more electric vehicles and maybe there will also be sea level rise in parts of the country, questions like this that are so yeah. So that's what we're trying to do, is to develop and think about what are all these implications. Yeah.
When I lived in Texas, there was a program through Houston Lighting and Power, commonly known back then as Houston Looting and Pillage, that you could sign up to have a system installed on your air conditioner, which is a fairly large proportion of the load for 6 months of the year in Texas. where the power company could actually turn it off for brief periods and turn it back on automatically, 20 minutes at a time. You know, the house did not heat up significantly. You didn't even notice it happening. Is something like that feasible as a way of lowering load when you have to shut off portions of the grid and route power to areas in a more roundabout way?
Yeah, so that's a really, I'm glad to hear that you were part of this demand response program, right? That's exciting. It is, so I think that, so actually it's kind of interesting what you're describing about your house and the house having an air conditioner and then being able to turn it off for like 20 minutes at a time. It's kind of interesting because when we think about these type of changes to the electricity demand, you can actually think about it a little bit like a battery. So you can think about the temperature in your house as essentially the state of charge of your battery.
Sure.
And if I turn off the air conditioner, the temperature is going to start increasing, meaning that you're kind of losing state of charge essentially. And the reason I'm mentioning the battery analogy is that just as with the battery, there are limitations to how long you can turn it off before you start being, unhappy as a customer. When we talk about these different types of flexibility that are there, they are all super important for a number of different reasons and to manage different kinds of aspects of the grid. So like, for example, in the context of renewable energy, having access to this ability to turn off power for a shorter period of time, if there's like, for example, a very steep decrease in the amount of solar power that is available around sunset. So these can be super important for the grid and really help manage and improve the way we use renewable energy. But then if you think about it as something that is going to go on for 3 days, then maybe this is less applicable, right? And so there's all these different time scales that we are thinking about when we are thinking about the grid. It really goes from like second to second balancing of everything, where the air conditioner can be super also helpful in that case, to sort of thinking about like, more like weeks and months and ahead.
And what do you do when the hurricane has just taken out all of your high tension lines?
Right, exactly. Yeah. So I think there's definitely this idea that if you have smarter devices, maybe that can help you also have more of a home system where you will maybe then also have the battery or a diesel generator. I mean, there are a not insignificant amount of people who have diesel generators at home, and so then it's if you live in an area like where there is public power safety shutoffs, and so these people adapt in order to become also more resilient to outages on their local level. So one of my concerns with this, if we are leaving it too much to the individuals, is that there might be people who are left behind, who can't afford it, who don't own their own house, they can't install, maybe they don't have space for a battery, they cannot install a solar panel, and so these are also important questions to consider.
May be relatively wealthy, but are apartment dwellers and don't have control over whether the building has solar installed, whether the building has a backup generator, things like that.
Right. Exactly. So that is also definitely, yeah.
Jim Lineweber's asked a couple interesting questions I'd like to pose to you. One was about the deferred maintenance. Do you have any insights into the deferred maintenance issues with the PG&E grid? And then a little further down, he asks, do you have any insights into what happened in Texas this winter?
Yeah. So I can speak more about what happened. So in terms of PG&E and deferred maintenance, I think that I think that is definitely an issue. It's an issue when the power lines are not being kept to standard. They are not being maintained at the level they should be maintained. I mean, this definitely then contributes to the fact that they can fail more easily. And I think there's stories about like the campfire, for example, being being started by very, very, very old line that probably shouldn't have been in operation at all. And so definitely these are concerns. I don't know enough details about that to sort of talk to it in super much detail beyond that. So again, I would just say that I think these are also questions for regulators to sort of try and figure out good ways of regulating this industry in ways that promote maintenance. So that, for example, if you say that a power company that has maintained a certain level of maintenance and replaced their components at a reasonable rate, and are doing their due diligence in terms of keeping their system running, maybe they should then be exempt from some of the liabilities, because some of these wildfire ignitions are also maybe beyond what the company could prepare for. I mean, it's kind of a very natural part of a power system, unfortunately, that these things will happen from time to time. In terms of Texas, that was so essentially, I mean, we all know that it was cold during that time. So essentially, the short story there is that there was this cold wave that came down to Texas. When you get very cold weather, you typically increase electricity demand because people also use electricity for heating. You also increase gas demand because also people use gas for heating. And what happened was that this increase in demand coincided with a massive outage of generation. And so essentially all the different kinds of generation technology that is there in Texas experienced some sorts of outages. So that went from wind turbines that were experiencing icing and had to be shut off because of that, to nuclear power plants that were also shut off because support systems that were freezing. But most significantly, the generation that normally acts as a very reliable source of electricity is natural gas. And natural gas is very, it's a great kind of generator to have in a grid because it is very flexible, and it allows you to sort of ramp up quickly if you have an increase in demand. So that can be a very good thing about a natural gas generator. However, most of these generators, they require natural gas to be supplied at the point in time when they are generating electricity from the natural gas pipeline system. And essentially what happened in Texas was that there was essentially no, the natural gas, the wellheads were freezing, and the natural gas to the power plant was curtailed. So the power plants just simply couldn't get enough natural gas. So that meant that there was about a little more than a third of the generation capacity in Texas in terms of was natural gas that was outaged during that period of time. And so that is, of course, I mean, this is so I think of this as sort of, again, one of these events where it doesn't happen very frequently, but you have like one sort of cause, which is cold weather, that causes sort of failures at many different locations, and these kind of effects where you get very high demand and very low supply of electricity. And there are questions about interconnections, the way the system is run, and all of this is unfolding. And I think it will be interesting to see what comes out of it, and hopefully they will prepare their power plants better for cold weather in the future. So this doesn't happen in Wisconsin, right? I mean, we don't have power outages because of cold weather in the same way.
Sandy Rotter and Diana Lutz, you both asked about burying power lines. Do you want to come on and ask that question? Make any comment, or you might be able to read it from the chat there also.
It's expensive.
Yeah.
My other question is underserved communities that I think we should be thinking about.
Okay. So I'd like to hear more about the burying of electric lines. If that's not an option, that's great, whether it's because, as Diana points out, they're eroding out of the ground or because it's expensive to put in the first place.
I think the main issue, I mean, cost is definitely a main issue.
So the thing that struck me in visiting Italy in 2017 was I did not see a whole lot of above ground power lines in many places compared to Madison, which is, if you want underground, you got to pay for it. And you can see where people have paid for it and where they haven't. This isn't a wildfire issue. It's a different type of issue. But I could sure see why, if it's very expensive, that's got to be part of your equation, and it doesn't bode well for large scale underground burying of wires.
Yeah. So I think that it's fair to say, like, I think urban areas in Europe probably have more undergrounding of lines than we have here. Some of this also might be due to different structure of the distribution network. There are different reasons. There might be a number of different reasons, but also here in Madison, right? If you walk, if you walk like really downtown in Madison, there's also much of the infrastructure which is underground. So that also happens here. It is sometimes a bit of a question of like, how dense is it? How many people are you supporting within a certain range of power supply? So there's interesting things that happen. So like one of the things that actually happen in Europe when you do have a lot of these undergrounded power lines in cities is that so traditionally there has system operators have been very concerned with having low voltage. But now that you have a lot of undergrounded lines, there is this concept called reactive power, which actually causes the voltages to increase. And because the undergrounded cables, they produce this reactive power. And so this is also, so there's a lot of there are different questions like that. I don't think that is necessarily the main issue, though it could be if you wanted to underground a very long line that really goes very far. Having these different electrical characteristics could prevent that from being feasible. There's only so many tens of kilometers of AC line that you can underground before you actually run into issues with it. And then you would have to think about putting up maybe a system that uses DC or another or lower frequency AC or something like this. And that is also has its own complications. So I think that would be on the transmission scale, maybe a more of a selective thing that you do in very high risk areas. But yeah, I mean, it could also be that we will see more undergrounding of distribution grid in areas where there's a lot of trees and high risk of ignitions.
Sandy and Diana, did this get your questions responded to? And Sandy, your question about lower income impacts.
Yeah. So lower income and underserved communities. I think that so this is one of the things that we saw in Texas, right? Is that you see when there was the big power outage. I mean, if you have scarcity of power, essentially there is not electricity available. Then one of the things that can happen is that you say there are certain customers that are more important than others. And that typically includes things like a hospital. And so if you want to keep power onto a hospital, then typically because of the way distribution grid is built, it means that you're also going to give power to people who live around the hospital, because you can't just give to the hospital. There's lines that go through the neighborhood. And so because of that, you then end up getting a situation where neighborhoods that have hospitals have better access to power during emergencies and situations with scarcity. And that can be concerning because these communities that have hospitals, I don't know, maybe they tend to be wealthier neighborhoods, or there are also neighborhoods that maybe, I mean, they lack access to hospitals, and now they're also going to lack access to power. So these are kind of concerning things that one need to be kind of careful about. And I think is a very important thing that we need to think about if we are, as we are starting to if we are going to see more of this type of scarcity of electricity, we need to make sure that those impacts are shared proportionally among people, and that they don't disproportionately fall on communities that are already that are maybe already disadvantaged. Yeah, and I also think that it's important that we think about, do hospitals really need that grid power, or do they maybe have backup generation? They might already have access to their own power because their power supply is so important that they need to have that already by themselves. So you could think about it: should we give power to the hospital, or should we give power to people so that they don't have to go to the hospital in the first place? And I think both of those are important things to keep in mind. That a hospital can get overwhelmed if the community around it is also, kind of running to the hospital because they are lacking power and need help.
Well, thank you very much. Sandy, thanks again for suggesting Professor Roald probably a year ago. And I'm delighted to have her now, especially in light of the many case studies that she provided to us. Bia, thanks for doing the technical stuff. And Professor Roald, thank you very much for coming on. We'll see everybody next week for David Lovelace's talk on the Triassic.
Yeah, thanks everyone
Thank you.
for
I'm
coming in for the